We'll now look at one additional set of examples involving radicals. We begin with several definitions. The first definition gives us the meaning of a to the 1 over n. And what we're going to do here is basically key in on this part of the definition right here that says a to the 1 over n is equal to the nth root of a. And what that is saying is that if I have an expression like a to the 1/5, that is the same thing as the 5th root of a. Or if I have a to the 1/7, that's the same thing as the 7th root of a. And so it gives us a way to take a base raised to 1 over a number and write that as a radical. The second definition says that we want to define the meaning of a to the m over n. And so here we're basically going to look at this part right here of the definition where it says a to the m over n is equal to the nth root of a to the m, which is equal to the quantity, the nth root of a, raised to the mth power. So what this is saying, to give you an example, is if you have a to the 3/4, this is saying that this is equivalent to the 4th root of a to the 3rd, or it's equivalent to the 4th root of a, where the quantity is raised to the 3rd power. And so again, it gives you a way to take a fractional exponent and write it as a radical. Our third definition discusses this scenario where we have a raised to a negative exponent that is fractional. So a raised to the negative m over n. And we have seen this scenario before, and we know that if our exponent is negative and we want to make that exponent positive, we simply drop it to the bottom of the fraction and write it 1 over a to the m over n, and our exponent remains positive in that case. So let's go ahead and start working on some examples. We have 5 examples, and we're told to simplify each of the following expressions. The first example is 27 to the negative 2/3 power, and it's kind of difficult there to see the negative, so I'm just going to rewrite that problem. 27 to the negative 2/3 power. Now, we have a couple of options in terms of writing this as a radical. We can write it according to our rule as the 3rd root of 27 to the negative 2. So we have that option. Or we could write it 27 to the 1/3 times negative 2. And that would also be an equivalent expression because we know that 1/3 times negative 2 is going to be equal to negative 2/3 as well. And if we do it this way, then we're going to be looking at the 3rd root of 27 raised to the negative 2. Now, if you look at your 2 options, this is kind of difficult to work with because in order to work this problem, we're going to have to take 27 and raise it to the negative 2 power. And so I'm going to eliminate that because I think that will be too difficult for me to deal with. And I'm going to come over here. What is the cubed root of 27? What number times itself 3 times is equal to 27? And we know that that's equal to 3, correct? Because we know that 3 times 3 times 3 is going to give me 27. And so that leaves me 3 to the negative 2 exponent. And we know that if we want to write this as a positive exponent, we have a rule that simply says take it as part of a fraction and drop it to the bottom. And so it's going to be 1 over 3 squared, which would equal 1 over 9 as our final answer. Part B of the problem asks us to find the ninth root of negative 8x to the 6th. So what we're going to do here first is we're going to rewrite the expression using some rational exponents. So in other words, we're going to break this up and look at the ninth root of negative 1 times 8 times x to the 6th. That's going to separate the negative from the 8. The next thing that I'm going to do is I'm going to rewrite the 8 as 2 to the 3rd. And I'm going to leave x to the 6th as it is. Now let's consider taking the ninth power of these if we can. We can take the ninth power, or the ninth root, of negative 1. We know that anytime we have an odd power on the outside, and we're taking that particular root of negative 1, that is just equal to negative 1. So that part is not going to cause me a problem. The rest of it, what I'm going to do is take it out of radical form. So we know that if it's a ninth root, it's equivalent to the 1/9 power. So I'm going to rewrite this 2 to the 3rd times x to the 6th in parentheses, and I'm going to raise it to the 1/9 power. I'm then going to distribute that 1/9 power to both of these exponents. So the 2 will become 2 to the 3 times 1/9, which will be 3 over 9. And the x will become 6 times 1/9 will be 6 over 9. So we're going to have negative, and I'm going to drop the 1 there, negative 2 to the 1/3. And we're going to have x to the 2/3. Now our directions ask us to put it back in the same format that we started with. So if we started with a radical, we want to end with a radical. So since both of these have a 1/3 power, I'm going to leave the negative on the outside, and I'm going to treat it as a third root. So this 1/3 power becomes a third root on the 2. And the x to the 2/3, remember, becomes an x squared underneath a cubed root. And so our final answer will be negative cubed root of 2x squared. All right, let's look at part C. Part C asks us to find 5x squared plus 3, that quantity raised to the 8/3, times 5x squared plus 3, that quantity raised to the negative 2/3. Now if you notice, we're multiplying here, and furthermore our bases are the same. So we have a rule that says that if your bases are alike and you're multiplying, your exponents should be added. So we're going to take 8 over 3, and we're going to add negative 2 over 3. So that's going to give me 5x squared plus 3 in parentheses raised to the 6 over 3 power, which is the same thing as 5x squared plus 3 raised to the 2nd power. Part D is asking us, and I have it typed out over here, to apply this property. So remember that if you have a 5th root of a cubed root of x squared, then you simply need to multiply your two roots together. So this will become the 15th, 5 times 3, root of x squared. And we're done with that one. And the last part of this problem, we have 5x minus 1. That is a quantity raised to the 1st power divided by the same quantity, 5x minus y, to the negative 1/3 power. And remember that we do know how to work on this. We know that either we're going to subtract the exponents or we're going to make everything positive and then deal with it that way. So if we're using our property here, we're going to say that 5x minus y, since that's our common base, and we're going to do 1 minus the negative 1/3. So 5x minus y, this will become 1 plus a positive 1/3, which would be 4/3. Our other option here would be to take this denominator and bring it to the top. Making that negative 1/3 power positive. And then you have bases that are alike, in which case you would add your exponents. So 5x minus y to the 1 plus 1/3, which would be 4/3. And either way there is appropriate in terms of working out this problem. Okay, we have one more set of examples. The book says that these are a bit more complex. So let's look at these two examples as we finish up this section. The first one asks us to find the fourth root of x squared. Well, remember that the fourth root is the same thing as a 1/4 power. So this one actually isn't too bad. The fourth root is the same as the 1/4 power, and so we have x to the 2 times 1/4 power, which would be 2/4, which would be 1/2. So we have x to the 1/2 power. Now, the only thing that is a little bit complex about this is that we have to keep in mind that the original expression here is defined for any x. I can plug any x into this problem and it'll work, because when I plug a number in here, negative or positive, and square it, it's going to become positive. So the original expression is good for any x value. But this expression, which ends up being equivalent to the square root of x, is not good for every x value, because remember that we cannot put negative numbers into that and then take the square root of it. And so in order to have this work out correctly, we need to add in an absolute value to be sure that that x value stays positive. And so our final answer will look like the square root of the absolute value of x. All right, in our last example, we have 3, the third root of 2, times the square root of 3. So let's begin by changing those radicals to fractional exponents. So the third root will become 2 to the 1/3, and the square root will become 3 to the 1/2. Now, eventually, I would like to be able to combine these exponents in some way, and I know that if I'm going to do that, they're going to need a common denominator. So let's go ahead and get a common denominator between 1/3 and 1/2. That common denominator would need to be 3 times 2 would need to be 6. So I'm going to be multiplying this first one by 2 and the second one by 3 in order to get that common denominator. So my first one becomes 2 raised to the 2/6, and the second one becomes 3 raised to the 3/6. Now, let's look at this in terms of a sixth root. So let's take it back to radical form. If we make a sixth root out of it, it would be the sixth root of 2 squared times the sixth root of 3 to the 3rd. So the sixth root of 2 squared would be the sixth root of 4. The sixth root of 3 squared, or 3 to the 3rd, would be 3 times 3 times 3 would be 27. Now, since they're both sixth roots, we can push them together as one sixth root, making it 4 times 27 underneath the radical. And 4 times 27 is 108. So our final answer would be the sixth root of 108.